Good day, students. Myself, Dr. Monika Khetarpal. I welcome you all in the lecture series of MSc Previous Physics. We were dealing with the first paper, that is Classical Mechanics. In our today's lecture, we will discuss about circular orbits. We will discuss the stability and closure condition of these circular orbits. We know that potential energy of a particle can be expressed as sum of potential which arises from central force and the term which is related to centrifugal force. Here I have expressed the total potential energy as V prime R and the potential energy related to the central force is expressed as V, which is a function of R, and this term VCR, this term is related to centrifugal force. And we already know that potential energy term of central force is L square upon 2m R square. Here m is the mass of the particle and the factor L, it is a constant factor and it can be derived from the well-known Lagrangian expression. In r theta coordinates, the Lagrangian of the expression is kinetic minus potential. Kinetic energy is half m r dot square plus r square theta dot square. Hence, from this expression, we know that a coordinate which do not appear in Lagrangian, that coordinate will be cyclic in nature. So, here in this problem, theta coordinate is cyclic and the momentum corresponding to a cyclic coordinate will be constant. The momentum formula is del L upon del Qj dot. Here the coordinate Qj, generalized coordinate is theta. Hence P theta will be del L by del theta dot. And I am assuming the constant generalized momenta to be expressed as small l. And from this I get small l to be equal to mr square theta dot. Now, the total energy of the system will be kinetic plus potential term. The kinetic energy is half m r naught square and we have expressed potential in the form of two terms, one arising from central force and one coming from centrifugal force. The total energy remains constant. And we know that circular orbits are always allowed. But there is a specific condition at which these allowed orbits are stable or they are unstable. Now we are going to determine the condition at which the circular orbits will be stable. For this purpose, we are drawing a graph between the effective potential energy and the distance r. So this is the graph between V dash r and r. And we are assuming that the central force follow an attractive inverse square law. So when the condition of attractive inverse square law of force is followed, the central part of potential energy contribution will be minus k by r. Here k is constant. And the contribution of centrifugal force which leads to a potential energy is L square upon 2m r square. This factor is positive always. So it is drawn on the positive side and the contribution from the central force is minus k by r. So it is drawn on the negative side of V dash R. Now we have to draw the effective component of these two potential energy. This is the effective component of the two potential energies. That means this is our V dash R. As we can see that this curve, it has a minima at R equal to R0. So this is our stable circular orbit. Now I am drawing another graph to show the difference between a stable and an unstable circular orbit. This is the graph which shows the effective potential energy with R. This is our central force contribution of potential energy. This is centrifugal contribution, and this graph shows the effective potential energy. We can see that in this graph there is a maxima at R equal to R0. So from this graph we can see there is no unbounded motion. So it is an unstable graph. Whereas in this graph we can see when V dash R is even, there are two turning points. One is this one and another is this one. So the motion will be bounded motion. It will no longer remain circular as it oscillates between these two values, which are termed as epicidal values. Now we will discuss the stability and condition for closure of these orbits. As we have already stated that potential energy will be the sum of potential energy from central force and the contribution coming from centrifugal force. Now, in order to determine the condition of stability, what is the deciding factor? We will determine the second derivative of our potential energy. Second derivative of effective potential energy will be determined. If this value is positive at R equal to R0, what does R0 means? R0 means the point at which energy is minimum. So, the condition of stability of circular orbit will be determined mathematically by the sign of second derivative of V dash, and this calculation is done at a point of minimum energy. That means the curvature of V dash versus R curve decides the stability of orbit. So we can say that if the second derivative at R equal to R0 is greater than 0, the orbit will be stable, and if the second derivative at R equal to R0 is negative, the orbit will be unstable. To clearly explain this, I am taking an example for this purpose, and I am assuming that my central force leads to a potential energy function which is given by Vr equal to minus k r raised to power n plus 1. Here k is constant. So using this Vr, my effective potential energy will be V dash R equals minus k r raised to power n plus 1, the central force term, plus the term which arises from centrifugal force. The centrifugal force term is L square upon 2m r square. Now I have to find the second derivative. So in order to find the second derivative, I am differentiating my effective potential energy. So first differential of V dash R will be del V dash upon del R. This will come out to be minus K n plus 1 R raised to power n, the first term, plus the another term will be minus L square upon mr cube. Now since at r equal to r0, V dash is minimum. So first derivative will be 0 at this point. I am substituting del V dash upon del R to be 0 at R equal to R0. Substituting R to be R0 and putting the term to be 0, I have obtained the value of a factor Kn plus 1. It comes out to be minus L square upon m R0 raised to power minus 3 minus n. Now I have already determined the first derivative. So again differentiating, I can get my second derivative. I have my second derivative in the form minus k n plus 1 r0 raised to power n minus 1 plus 3l square upon m r0 raised to power 4. In this term, I am substituting the value of k n plus 1, which I have obtained as minus L square upon m r0 raised to power minus 3 minus n. Substitution gives me L square upon m n plus 3 r0 raised to power minus 4. Now, since we have already discussed that for stability, second derivative must be greater than 0. That means the second derivative of potential energy must be positive at a point at which energy is minimum. That means at r equal to r0. So, this factor will be positive only when, from here we can see, only when n is greater than minus 3. So we have obtained the condition that circular orbit will satisfy the stability condition only if the factor n is greater than minus 3. So in this manner we can judge the condition of stability for a given central force. Now another thing which we have to determine is the condition for closure. What does closure mean? An orbit will be closed if it retraces its path. That means the path which has been earlier followed will be repeatedly followed. Attractive central forces, for as we have discussed in this example, they will produce circular orbits, and all circular orbits are closed orbits. The condition requirement is that when the central force exactly equals the centripetal force, this condition must be followed when the central and centripetal forces are exactly same. The non-central forces do not produce circular orbits, and all bound states are closed only for the inverse square law of Coulombian or Newtonian type of forces. Hence, the stability condition will be that the second derivative of potential energy must be greater than 0, and closure condition is that the forces must be attractive central forces so as to be obtain the property of closure. Thanks a lot for watching.